Okay, so I'd like to thank Bernard for this kind invitation. It's always a pleasure to be back in Paris. So today I'll tell you about forces in non-equilibrium systems. I'll mostly talk about pressure, but I'll also discuss forces in more general. And specifically, as you'll see after the introduction, I'll focus on really osmotic pressures. So this is work that we've been doing over the last few years already, and it's been evolving slowly. Most of the work has been done with Alex Solon, who's now at MIT, Julien Taillot from Paris, Meran Kardal from MIT, and Mike Cates from Cambridge, and then a bunch of other people. And what I'm going to do, the outline of this talk is as follows. First, I'll give a very, very basic introduction to what we mean by an equation of state. And specifically, I'll focus about an equation of state for the pressure. Once I'm done with this very, very basic introduction, I'll set the stage and I'll try to argue why there's a window where things might be interesting in non-equilibrium systems. And then I'll go on to explore this window. And I'll specifically study a class of systems that's called active systems. These are systems that are driven out of equilibrium by driving each of the individual particles out of equilibrium. I'll explain it later. That's in contrast to driving a system out of equilibrium, for example, by the scenario we just heard about, where you couple it to two reservoirs at the two ends. Then I'll discuss the models that we've been playing with and studying. And then I'll discuss the interesting behavior of equations of state, which are grayed out for a specific reason here in these active systems. And I'll discuss both non-interacting, which are interesting even the non-interacting case is interesting. And then I'll go on to discuss the interacting case. And then, depending on how much time I have, I'll discuss other properties of forces in active systems. Okay, so I'll start with reviewing something that's very, very, very basic, the concept of an equation of state in equilibrium, and specifically for the pressure. So the most well-known equation of state is the one for an ideal gas. The pressure is given by the energy density in the system up to a factor which is, in 3 dimensions, 2/3. Or we could write it as the density of particles in the system times the temperature. The things that we take for granted when we write these expressions, sort of without thinking after a while, is that the pressure really only depends on these systems on bulk properties. You tell me some bulk property of the system, and I'll tell you what the pressure of the system is, even though the pressure or forces exerted by a system stem from the interaction of the system with some wall, container, or something embedded inside the system. And what we know from equilibrium, and I'll just review it in a second, is first of all that no matter what wall we put on the system, and that's sort of hidden in the fact that we're saying an equation of state, if we put a soft wall, which is, say, a gel, or we put a wall, which is a metal, the pressure on the wall is exactly the same. The container doesn't change anything. Another thing is that if we take a sphere, or we take a box with sharp angles, the pressure on the walls is independent on the shape of the potential of the wall. So no matter what wall we take, the force acting on the wall, normal to the wall, is independent of the shape of the potential. And what I'll do in this talk is sort of review this for non-equilibrium systems. So let's, again, just give a very rudimentary introduction to equation of states in equilibrium. And for simplicity, the whole discussion and the introduction will assume that we have a very, very simple flat wall at the edge of the system. You can generalize all these discussions, of course, to more complicated settings. The most simplest definition of pressure comes from thermodynamics. We take a system, and then we move the wall. We move a wall a bit. We perform work on the system. And the change in energy of the system is given by the work that the system has, the change in energy of the system is given by the work that's been done on the system. And if we move a wall, that's given by the pressure times the change in volume. Because energy is an extensive quantity, then of course it doesn't care about the walls of the system. Then when we differentiate the change in energy with respect to the change in volume, all information about the boundaries of the system in the thermodynamic limit are completely lost. And this implies that whatever wall we put at the edge of the system, as long as it's a very narrow wall compared to the size of the system, the pressure is independent of the wall of the potential. Again, if we have a gel or we have a metal, the force on the wall doesn't matter. And you can use this argument also to argue that if I take a spherical container, if I take a rectangular container, or whatever I have, the pressure is again independent of the wall shape. There's another way to think about pressure, which is independent of using concepts from thermodynamics. It's just calculating the force that's acting on the wall holding the system. So we think about a system containing some many-body system, and we put a potential at the end of the wall. This potential is marked by this potential, which starts at some, say, position L, which marks the edge of the system. And what we do is we calculate the thermal average of the force exerted by the particles. This is the density of particles at point X on the wall at point X. So that's what you would define as pressure, you know, at the beginning of high school without knowing any thermodynamics or anything like that. And it's easy to check that this works for an ideal gas. We know that for an ideal gas, the density of particles inside some potential is given by the density times e to the minus beta the potential. And you can see that this expression is now in equilibrium a full derivative. And if you carry out this full derivative, you find out the usual equation for an ideal gas. So this is just a rederivation of something we know. It's actually very, very simple. I think I'll skip it because it's so simple. I'll go through it very, very quickly. It's very, very simple to write down the definition of pressure from thermodynamics as a derivative here of a free energy, and use the definition of a free energy, and just introduce the potential explicitly in the partition function. So the free energy, just to remind you, is minus the temperature times log of the partition function. And if I introduce the potential that's modeling the wall explicitly inside the partition function, it's a really three-line calculation to show that the definition of pressure that comes from thermodynamics and the definition that comes from the force acting on the wall are completely equivalent. And of course, this better be the case, otherwise the whole thing would be useful. So again, just to reiterate, I'll say this again and again because this is sort of leading to the punchline, that the force acting on the wall does not depend on the potential. So to summarize this, again, rudimentary introduction, we know that in equilibrium, the pressure always admits an equation of state. No matter what systems we're modeling, we always have an equation of state. It goes without saying. There's another reason why we often have equation of states, and that's when we have momentum conservation in the bulk of the system. So if we take a system which has momentum conservation in the bulk of the system, we can write down, and again, I'm considering just okay, this is general, but I just imagine a one-dimensional wall with a one-dimensional symmetry along, say, the y direction. And I write down an equation for the momentum density inside the system. So the equation for the momentum density, if the bulk is conserving, obeys a continuity equation. So this is minus divergence now of a tensor because P is a vector. But again, just think about the one-dimensional geometry to keep things simple. And then, of course, when a particle hits the wall, it obtains momentum from the wall because the wall is exerting a force on the system. And therefore, we have a term that's accounting for the fact that the wall is changing the momentum of the particles. And now what I'm going to do is look at the pressure. And the pressure, as I've argued before, is given by an integral over the density times the force. So this is just the definition of the force acting on the wall. I just want to stress that, of course, the current here can be a noisy object. And then I just have an average of the current. It doesn't change any of the arguments that I'm writing here. And what I do is I just look at the steady state. So the left-hand side is 0, and I'm left in this one-dimensional geometry with, again, a full derivative of the momentum current. And I'm just left with a momentum current in the bulk. And this, again, if you use this argument, you find out that you essentially, if you do the calculation for an ideal gas, you essentially get the same result, that it's proportional to the energy density in the system, the pressure. So again, if we have a bulk conservation of momentum, of course, forces are related to momentum. And what the simple argument shows you that if we have bulk conservation of momentum, then automatically you have an equation of state, of course, assuming that the bulk admits some uniform steady state that's not influenced by the boundary, and out of equilibrium that might be the case. Okay, and this is irrespective of the system being in equilibrium or out of equilibrium. This is a very general argument. So just to recap, in equilibrium we always have an equation of state, and this is true with this new thought about momentum, irrespective if our system conserves momentum or doesn't conserve momentum. There are cases where the wall doesn't act as I've specified below. It doesn't. It's not the only momentum source in the system, or sink if you want. Osmotic pressure is a great example. When we have osmotic pressure, we can have fluid moving through a membrane, and then there's no explicit conservation of the whole momentum inside the system, because momentum can flow across the membrane. There are other examples. You can think about particles moving next to a surface, and that's actually relevant in systems, say, of granular media, which are moving on a surface. And therefore, we have no explicit momentum conservation. If these systems are in equilibrium, then equilibrium guarantees that there is an equation of state. But if we're out of equilibrium, the question is, if I don't have momentum conservation, do I have something new with respect to the properties of forces and pressures in these systems? So just to recap, because I think I've said it in a slightly confusing way, in equilibrium, no matter if we have momentum conservation or not, we always have an equation of state. Momentum conservation guarantees an equation of state, but there's a large class of systems which have no momentum conservation and are out of equilibrium. And the question is, in this window, do we have some new novel behavior? And the purpose of this talk will be to argue that yes, in this window of opportunity, there's a lot of very rich behavior that doesn't occur. And therefore, really, the title of my talk should have been osmotic pressures. But again, I'll show some, hopefully I'll get to some results, actually experimental, for one of the things that I'll show, which are for particles next to a surface. Okay, so with this introduction, I want to motivate the systems that we've been looking at. And the class of the systems falls into, by now, something that's a whole field of non-equilibrium system, class of non-equilibrium systems, which are called active systems. And what roughly separates them from the other classes of non-equilibrium systems that you might have seen is that here each particle is consuming energy to perform motion. So really, each particle is driven out of equilibrium on its own. So there's actually a whole slew of motivations for studying these systems. A lot of it comes from biological systems, and these grow in levels of complication. And what I want to show you is probably the simplest one. This is just a gas of E. coli bacteria. So E. coli is a bacteria that lives inside our gut, and its size is about a micron. And it performs this funny motion, I'll show the movie in a second, where the bacteria roughly swim in straight lines. They have these flagella, which are push them inside the fluid. I'll skip the details because it's irrelevant. But they move roughly in straight lines for 1 second, and then in about once every second, the bacteria stop, these flagella move, open up, and the bacteria reorients itself. So if you look at these bacteria, you track one of them, then you can see that it's swimming, stops, picks up a new direction, et cetera, et cetera, et cetera. So they have this motion that is, to first approximation, like a simple Derrida model of particles. They're moving with some ballistic velocity, and then they stop, they scatter to a new direction, and move again and again. Again, this system is, the particles are small enough, and if you calculate the Reynolds number, inertial effects are completely negligible. By now, motivated by questions of self-assembly, etc., people have been playing with artificial systems which have similar behavior. And these are self-propelled colloids. There's by now a whole slew of these particles that are generated in labs. And again, their size is about a micron. Their velocities are, again, 1 micron a second. And these particles are such that they're driven out of equilibrium by a chemical reaction occurring at one end of the colloid. Again, I'll skip the details because they're not so important for what we're talking about. But what you see in this movie is a bunch of colloids. And initially, you're just looking at them, and they're in equilibrium. So initially, what you'll see in this movie is these colloids diffusing inside the solution. And then after a while, UV light is shined on this sample, and this UV light drives the chemical reaction at one end of this colloid, and you'll see that it starts moving in this roughly ballistic manner. So this is, again, just usual Brownian motion, and then we turn the light on, and these guys start to move ballistically. Of course, there's some noise, so there's some gradual change of direction of these particles inside the fluid. And again, there's a whole slew now of experiments studying these systems with the aim of, there's many, many aims, but one of it is really to use this for some sort of self-assembly. What I want to stress is that both systems, both the E. coli, because it's eating and using this food to move inside the fluid, and the colloids, which are using the chemical reaction at the edge of the colloid, both are out of equilibrium. And the steady state, if we look at this, it's completely boring. It looks like an ideal gas. If I look at it from far away, it's just a fusing particle. In principle, nothing exciting should be hiding in these systems. But nonetheless, I'll argue that there is something interesting. Okay, so the question that we set up to study is, okay, we have these systems. Let's look at the equation of state. Let's calculate the equation of state for these systems. So let's calculate the pressure. And of course, these systems consume energy and dissipate it. So we can't use the usual definition from thermodynamics. It doesn't make sense. If I'm looking at osmotic pressure, there's no conservation of momentum. So the only definition of pressure which I can use is actually calculate the force acting on the wall. So the idea is very, very simple. Take a system of these active particles, put some potential at the end of the system, which is in this cartoon drawn as a spring, calculate the density inside the wall. You don't actually have to do it technically, but I'll skip these details. Calculate the density inside the wall, which is now a non-equilibrium steady state. It's not a Boltzmann distribution because these systems are driven out of equilibrium. And all I have to do is calculate this integral. So the task is fairly simple. And again, this recipe works for any active system any system that you might work on. But again, my definition for pressure is the force acting on the wall. So now I want to show you the class of models which are directly motivated by the experiments I've shown you. And these are, again, active matter. And I've now added the word dry, stressing that there's no momentum conservation. Okay, so people, that's just terminology. When we say dry active matter, we should mean that there's no momentum conservation. And again, this is relevant for osmotic pressure, which is what you would measure for bacteria, for example, or for particles next to a surface. Okay, so the models that I'm going to discuss, I'll discuss them in 2D. You can generalize everything to 3D. Doesn't change a lot. It doesn't change the results in a significant way. I'm going to study a class of models which fall into what people call run and tumble particles and active Brownian particles. And the idea is that if you want motivated by the E. coli, we have these ellipses that are swimming inside the fluid. So each of these ellipses has an arrow which is pointing in the direction that it's swimming, and this arrow can rotate. So if you want, you can think about it as XY spins that have been liberated from the lattice and move in the direction of the spin. And there's some dynamics associated with these particles, some which is related to the swimming direction and some which is not. So the one that is related to the swimming direction, it can perform either, it moves with a velocity that depends on the direction of the arrow. And for what I'm going to do now, again, this has no significant consequences if you change this. The magnitude of the velocity will be assumed to be constant. So it's swimming in a constant velocity in the direction of the arrow. This is the activity. When I turn this guy off, I better be back at equilibrium. Okay, so this is my tuning parameter for if I'm in or out of equilibrium. Then I'm going to add tumbles. Remember the E. coli bacteria, they stop and they change direction. So I'm going to allow with some constant rate the particles to reorient with a random jump. So for particles which perform this tumbles, they move in a straight line. This is roughly a cartoon. Move in a straight line, choose a new random direction with some rate, a new random direction. So this is a typical trajectory of these run and tumble particles. Then I'm going to also allow for rotational diffusion. So rotational diffusion is when this arrow slowly performs diffusion. And these are called active Brownian particles. There's no tumbles now. And a typical trajectory of these guys is just it's moving in the direction of the arrow, and slowly the arrow is changing direction. So this is active Brownian particles, just words. And on top of that, I'm going to add diffusion of the center of mass of these guys. So these guys are performing some diffusion. So to calculate the pressure, I've told you that I'm going to calculate the force exerted on the wall. Then I want to consider what happens near the wall. What I want to stress that for both these models, whatever boundary conditions I impose, they're so simple that the bulk is dead boring. Nothing that I do at the boundaries is going to affect the bulk. Sorry. So in the presence of the wall, I have to describe the dynamics inside the wall. This is a slightly confusing picture, but I'll try to explain it. So this shades of blue signal the place where the wall potential is present. So you could imagine a half harmonic potential, which is increasing in this direction. And this is one of my particles that's sitting inside the wall. And what I have to do to specify its dynamics, I'll look at non-interacting now, is just specify the dynamics of the center of mass and then specify the dynamics associated with the angle degree of freedom. And once I've done that, then I'm done. So the dynamics that I have for the center of mass is, first of all, I have this activity. This is the thing that drives me out of equilibrium in the direction of the arrow. If I'm inside a potential, then I feel a force from the potential. So this guy is the force from the potential. This is the usual thing that you would find in Brownian motion. And of course, we have the diffusion of the center of mass. So this is just a simple extension of what we know from Brownian motion. The other The other dynamics that we have to specify is associated with the angle of this arrow. And the angle, first of all, I'm going to assume that it can perform a rotational diffusion. So this term signifies rotational diffusion. But on top of that, because I've put an ellipse, again, motivated by bacteria, but this is a very, very general property of things moving inside fluids. If I look at an ellipse inside a wall, there's a different force acting across the ellipse, and therefore the ellipse feels a torque. Okay, so if the ellipse is pointing parallel to the wall, then of course there's no torque. If it's normal to the wall, then of course there's no torque. But if I'm at some angle between them, you can guess that it's sine to theta just by general arguments, that it should be the leading order behavior of this guy. So there's some torque acting on this particle, and you can add tumble rates. I'll skip the movie. I have a small movie showing you that bacteria actually perform these. They feel a torque when they approach a wall, but I'll actually skip it. So just to make it concrete, I'm going to take a truncated harmonic wall. So this is a half harmonic potential, and I'm going to take an ellipse. So the potential, the only thing that you have to try to remember is that the strength of the potential is given by lambda, and the ellipse exerts a torque, which is related to how much asymmetric the ellipse is. And it's given, as I said before, for an ellipse and a half harmonic potential. It's so simple that it's just sine to theta. More complicated potentials, of course, something more complicated will be present. So what we want to do is calculate the pressure. What we actually do is we don't have to calculate the full probability distribution. You can actually get away by a trick by looking at moment expansion of the master equation. Okay, and that's our working tool for most of these calculations. And what we find out is the following expression. So first of all, we have that the pressure is, again, it's non-interacting particles at the moment, so it's proportional to the density of particles. We have a contribution, which we expect, which is not related to the activity. So I remind you, V is telling me if there's activity, if I'm driven out of equilibrium or not. So when V is equal to 0, I better be back at equilibrium. So I have a contribution, which is just the ratio of the diffusion coefficient of the center of mass and mobility, which is just the temperature. So this is the normal behavior for my ideal gas. And then I have another term, which you might as well guess without doing any calculation. If I look at this gas from far away, they're just diffusing about, and there's an effective temperature, and I can guess from dimensional analysis the temperature is given by the velocity square, which is the magnitude of the activity, divided by the mobility times either the rotational diffusion coefficient or the tumble. So this is an effective temperature. This goes along the idea that if I coarse grain, it looks like a diffusing gas, it's a diffusing gas. The surprising term is actually this guy. It's proportional to the activity. So again, it goes away when the activity goes to 0. There's some constants here which are not important. The important thing is that it's related to an integral of the torque, sine theta, which is again the angle which the particle is moving, and the density of particles, at position x at angle theta, and this is of course inside the wall because that's where the torque is non-zero. The striking thing is that both the torque and the potential and the density, of course, depend on the potential inside the wall. Okay, and that means that when I have a torque acting on the particles inside the wall, which is again very generic, the pressure depends on the exact shape of the potential inside the wall. That means that if I want to tell you what's the force exerted by these active particles on the wall, you have to tell me the whole shape of the potential. You can't just resort to telling me some bulk property like you could in equilibrium or when you have momentum conservation. So there's no equation of state for these things, And the pressure really is not just a function of the density and some other quantities. You have to tell me everything about the wall, and we're going to explore some consequences of this thing. Okay? The only case where the pressure doesn't depend on the wall potential is that when there's no torque, and in this case you have an equation of state, and this, just the fact that in this case the theory simplifies has attracted a lot of attention, because you might make maybe a sensible thermodynamic theory at some point of that case. Okay, so just to illustrate this explicitly, you can do there's a slight approximation done here, but you could take the half harmonic potential an ellipse and calculate the pressure acting on the wall, and you find out that it's given by this expression. The important thing to keep in mind that it's related essentially to the dimensionless parameter as this one, which is related to the magnitude of the torque. And what you see here is the pressure as a function, if you want, of the wall strength for a given shape of the ellipse. And what you see, and this is normalized, so it's 1 when you have a sphere. And what you see is that as I increase the wall strength, the pressure goes down rather dramatically. It's not a small change. It really can be of orders of magnitude, the change in the pressure. So the pressure depends on the wall strength, and this is again just an illustration of the fact that you have to tell me the details of the wall to know what the force acting on the wall is. And if you think about the system once you see this result, when you think about it a bit, it's easy to understand why this is the case. When we have more torque, the particles tend to align normal to the wall, and therefore the stronger the wall potential, the stronger are the forces that are aligning the particles next to the wall, and the less they penetrate the wall, the particles. Therefore, the wall is influencing the ordering field of these arrows inside the wall, and that in turn leads to dependence of the pressure on the potential. Of course, you can play a game. You could wonder if it's always that the pressure goes down when the wall becomes stiffer, but you could play a game by placing the arrow along the short axis of the ellipse, and then you find out that the pressure actually increases just by the same reasoning, because when I align the ellipse normal to the wall, the arrow is now pushing it deeper inside the wall. So the pressure can either go up or down with increasing wall stiffness depending on the wall potential. And I'm not going to discuss it here, but we actually have some funny examples where you could have, when you can have a pulling force exerted by the fluid. So just to recap this part of the talk, it's well known that if you take thermometers, sort of some fluctuation dissipation relation, and you measure the temperature in systems out of equilibrium, they don't agree. There's no reason for them to agree if you want. And here we're saying that this is true even for osmotic pressure. So if you measure osmotic pressure on these non-equilibrium systems, if you would buy the probe from different companies, you would get a different reading just because the probes are made differently. Okay, so far, lack of equation of state. This is the dead boring case of no interactions. And what I want to do is look at interacting cases, at least briefly. And what I'm going to do is I want to just understand the effect of interactions. So I want to look at a system which has an equation of state with no interactions. This is the case of spherical particles with no torque. And then I'm going to add interactions and ask if I retain an equation of state or lose an equation of state. And I'm going to look at 3 illustrative cases. And the first case is a very well-studied model. It's a class of models that falls under the name of the Vichik model. It's when these particles move, and if they're close enough to each other, there's some aligning interaction between the particles. So that's, again, like these XY spins that I've released and allowed to move inside the fluid. So there's some aligning interactions. In the model that we've looked at, that's the only interactions. There's no hardcore or anything else. And what I'm plotting here is the pressure as a function of density for 3 wall potentials. Again, these are semi-harmonic. It doesn't really matter. And I'm plotting the 3 curves for pressure as a function of density. And if I had an equation of states, all these curves would collapse one on top of the other. But the fact that for each wall potential I get a different curve directly illustrates that the pressure depends on the potential. So again, when I put these aligning interactions, then I lose the equation of state. Another very well studied model, it's used a lot to study collective behavior of bacteria. So bacteria tend to change their dynamics because of some other neighboring bacteria. So it's called quorum sensing. And a toy model is that the velocity of the particles depend on some local density of particles around it. So you could do different definitions of the model. It doesn't really matter. The important thing is that you integrate over some area around you, say with some Gaussian envelope, and you estimate the density, you calculate the density inside this region and modulate your velocity according to that. And again, we plot the pressure as a function of density, and we find that for different wall potentials, we get different behaviors, and therefore we have no equation of state. The final case, which has an equation of state, involves just pairwise interaction. So we take spherical particles, which have an equation of state, and we add pairwise interactions between them. And we plot, in this case, we plot the pressure as a function of density for more than 3, quite a few wall potentials. And you see that they all fall on top of each other. And that means that in this case, there is an equation of state. We can actually derive the equation of states, meaning that we can write down the pressure in terms of bulk correlators of this model and check that the equation works fine. Today, we understand that this is related effectively, the fact that we have an equation of state in these models is related effectively to, there's an effective momentum conservation in these models, despite the fact that the underlying microscopic model does not have momentum conservation. So far, for generic active fluids, there's no equation of states. And we saw that there are exceptions, so we need a test. So this is a sort of funny test for checking if your fluid has an equation of state or not. So this is an experiment where you take, say, an equilibrium fluid, and you put the membrane inside, and you put the membrane with one side of the membrane, say, a gel, and the other denser gel. And if you put it inside of the system in equilibrium, the pressure is equal on both sides, and therefore this partition stays static. And what I want to do is show you a movie of this thing for these active systems. And what you can see is that, so we have a soft potential here and a hard potential here. And what you see, if I just run it very quickly again, is that the wall, which we assume here to have overdamped dynamics, is just moving ballistically to the right. And then it stops at some equilibrium position. I'm going to show you the equilibrium position, which depends on the specific details of the wall potential. And for harmonic potentials, we can actually calculate the location of the wall for this simple model. So you just place an asymmetric membrane inside this active system, and you see if it moves or not. And that's an indication if you have an equation of state or not. This is sort of pushing forward the notion that there's no momentum conservation, which is important here. If we take this active fluid and we put it inside 2 containers, one with again, a very dense gel and a very non-dense gel, and we want to hold this whole construction in place, then we find out that we have to exert different forces on the 2 sides. And this is, of course, in any momentum-conserving world, will be completely silly. Okay, so So far, lack of equation of state due to wall potential. And again, the highlight is that in this window of systems where you have no momentum conservation and you are out of equilibrium, then you lose the notion of an equation of state for pressure. What I want to do next is discuss the effect of the wall shape. And people have been playing, this is from the Di Leonardo group in Rome, and people have been playing with putting different, so this is some ratchet wheel placed inside bacteria, fluid containing bacteria. The scale is, this is 10 micrometer. And what you can see is that sort of there's this ratchet effect where the bacteria are on average turning this quote-unquote motor in a given direction. So people have been playing with this it's cute, and I don't know, maybe you could do something useful with it. And what I want to do is ask, okay, so if we take a gas of bacteria and we calculate the force on the wall, what do we see? And again, so far everything was for a flat wall, and now I'm going to look at a non-flat wall. And again, to isolate the behavior that's really due to the curved wall, I'm going to look at spherical particles. So this is really the case where I look at a flat wall, I have an equation of state, and if anything funny is happening, it's only because of the shape of the wall, nothing else. It's not because of the torque. So what we did is we just took the same setup that we had before, but now with a wall potential which has some shape, and I'm going to start with this sine wall potential which has an up-down symmetry. It's already been known from several works that if you take these active particles and you put them next to curved walls, they have a non-trivial density distribution. And in contrast to equilibrium, where you only care about the potential, here there's a non-trivial density distribution. So we sort of expected something interesting. And indeed, we find, so this is the wall. The dark blue is the wall. And this is, in this case, non-interacting, but everything we do holds also for the pairwise interactions. And what I'm plotting here is the density of particles near this sine wall. And the dark red means that there's an accumulation of particles inside the wall. And here there's actually a depletion right outside the wall. And here there's an accumulation just outside the wall. And in fact, when you put these sine walls next to the system sort of shouts that it's out of equilibrium, and you immediately also generate currents inside the system. So right next to the wall, if you calculate the average steady state current, you find out that there's vortices which are driven next to the wall, and the direction in which they're driven depends if you have run and tumble or active Brownian particles. So this immediately shouts that it's out of equilibrium. And the combination of this thing, here I'm showing it for very, very steep wall potentials. And the only reason I'm showing it for steep wall potentials is that then I can define a normal to the wall in a coherent way. And what we find is that the pressure on the wall now depends on the position along the wall. Actually, the pressure is highest here and lowest here, despite the fact that for non-interacting there's a depletion here and an accumulation here. Right inside the wall, it's actually opposite. And so this is the pressure along the wall. And if you go to weaker potentials, you find out that it also depends on the exact shape of the potential. But then I have to do it in the x and y direction separately. And there's an interesting result that actually if you take the pressure and you average it over one period of the potential, then you recover an equation of state for the average force on the wall. So if you look at the force acting along, so let me go back, if you calculate the force, if you integrate the force acting along one period of the potential in the x, it's now only, for this symmetry, it's only in the x direction, then you find out that it obeys an equation of state. And that again can be related to, when you do this, you have an effective conservation of momentum. So the next obvious thing to do, if you have a non-equilibrium system and you put a potential that has no up-down symmetry, then by, I guess 30 or more years of work on ratchets, you expect some current along the wall. So what we did is, again, put some, so this is two walls at the two edges of the system, which now lack this up-down symmetry. And what you find out is that indeed, this is in blue here, there's a current that's now flowing across the edges of the system. So it's sort of an edge current running along the two edges of the system. And probably more interesting, you find out that there's a relation force that's acting on the wall that's in the direction of the current and with an opposite sign. So you find out that you put this, these walls on the system and there's an effective shearing on the edges of the wall because of its being out of equilibrium. And in fact, it's not very hard. You can actually show that, again, for these, this result holds for spherical particles or for particles with pairwise potentials. More generally, it does not hold. But you can show that there is a very, very simple relation between the total force acting on an object inside this active fluid. So you could take some, I don't know, some triangle inside this active fluid. It will generate currents around it. And there's a simple relation between the currents flowing because of the shape of this object and the total force acting on it. And they're related by the mobility of the particles inside the fluid and a different sign. Okay, so again, this is just, again, one of these ratchet effects that you put some asymmetric object, it's being pushed, and there's a simple relation between force and current. The last thing how much time do I have?
10 minutes.
Okay, more than I need, I think. Okay, so the last thing, okay, if I have more time, I might discuss more things. The next thing I want to discuss is a polymer, and I'm going to take, just to make this slightly more interesting, the polymer that I'm going to look at will have both bending and stretching rigidities, so it costs to extend its length and to bend it. And I'm going to put it inside an active fluid. So there's an active fluid here, there's an active fluid here, and there's a, in my two-dimensional system, it's a polymer. In a higher dimension, it will be a membrane, which we haven't looked at yet. And you could imagine that very, very quickly, I'm going to show a movie soon, that very, very quickly, you'll have some instability that will cause some modulations of this polymer inside the active fluid. And remember that I told you that if you have a wall with some shape in an active fluid, that the pressure is no longer uniform. In fact, if I look at some vertex here, then I find that there's a higher pressure on this side, then there's a higher pressure here than here, which means that there is a higher pressure here than here. So there's an inherent mechanism for an instability of these things inside a fluid, because a small fluctuation will generate an imbalance of forces on the polymer. And you can actually do a linear stability analysis and find out that there's some critical wavelength for this instability. I'll skip the details. And I just want to show you sort of probably more interesting than me talking, is a movie of this instability. Again, you don't see the active fluid, and there's some dynamics which we don't fully understand at the moment, where the wavelength of this initial instability grows slowly. Oops, sorry, this I didn't want to show you yet. Okay, you saw it, so I'll explain it later. I lost my cursor here. Okay, so there's some dynamics which cause this instability to grow into the longest wavelength. And in fact, a couple of months ago, we got this picture from Olivier Duchot's lab. And what he does, he takes metal beads on the surface and he shakes them. So this is a shaken granular media. And he takes the particles so they have asymmetric legs. So if you track the motion of each of these plates in the system, you see that they perform roughly motion like in active Brownian particles. They move in a preferable direction, slowly changing their orientation. And what he did is put a necklace in the middle of his system, and he assures me that this is a typical picture. So he hasn't picked up the one that looks the nicest, and you can see that indeed this instability shows up with now these are interacting, so there's an accumulation of particles here and a depletion of particles here, which is sort of similar physics to what we've discussed before. And the next thing we set up to look at is what we did is very, very similar, but we just released so we just released the particle from being anchored at the edge of the system. So what we did, we took polymers of different length inside an active bath. This has been done before, for example, by the group of Ralph Metzler, but people just observe things, and we think we understand the physics well now. And remember, there's a critical wavelength for this instability to occur, and this will manifest in the movies that I'm going to show you. So this polymer here is smaller than the critical wavelength. This is one half of the wavelength of the instability. This is one wavelength, and this is longer. And what you can do is you can observe the behavior. If it's very, very short, then it's just diffusing about as you would expect. If it's half a wavelength, then you have the instability kick in, and then this polymer moves itself like an active particle. So it spontaneously, okay, it's not a real breaking of symmetry because eventually it changes the direction, but it bends in one direction, and it starts moving because of the imbalance of forces on the two ends, and it's acting like an active particle on itself. And now if you focus on this guy, then this is one wavelength. Let me run it back. This is always, okay, let me run it backward. If you focus on this guy, so it's longer, and you can see that once in a while it has an instability, and there's a small rotor that's created, and of course the fluctuation destroys it, but it starts rotating again because the imbalance of forces on it. And eventually, if you take a very, very long polymer, then what happens is that the different forces just crumple it, and it just doesn't move at all. So actually, if you measure the diffusion coefficient, which I should have brought the graph, if you measure the diffusion coefficient of these polymers as a function of length, there's a sharp peak at a given length because of this behavior. Okay, so let me go back to the presentation. Okay, so you can ask if there are other differences besides what I've shown you, and just very, very quickly, because I think I should stop. For example, one of the hallmarks of pressure and equilibrium systems is that it's isotropic. That's even if the sound speed is different in different directions along a crystal, the pressure is always isotropic. And you can ask what happens in active systems. And it's been known that if you have a non-isotropic bulk state of the system, you can find discussions of examples like this in the review by Marchetti et al. And then you can have a non-isotropic pressure. But we were able actually to cook up a very, very simple example where the bulk is completely uniform and boring. If you look at the bulk, there's complete isotropy. All you have to do is modulate the velocity with pi, and we modulate it with pi so there's no bulk drift of the system, which will cause a non-trivial, a non-homogeneous steady state. And you find out that in this case, in fact, you can derive a simple expression for the pressure. The important point is that the pressure now depends on the angle, despite the fact that the bulk is on the face of it boring. And the last thing that I want to say is that usually in equilibrium, when we have no external forces and we have a flux-free state, this implies that we have a homogeneous state. This again, I think, really pushes the fact why momentum is here. So what you could do is you can play a game where you have two different velocity at two sides of a container, so different amounts of light in the experiment from that I showed before. Actually, I should have said from the Dave Pine lab. And you can actually show it's very easy that there's no flux in the steady state, but nonetheless, there's a non-uniform steady state. And this is true also for the interacting case. So just to summarize, again, we have this window of non-equilibrium and no-momentum conservation where interesting things can happen. And in these dry active systems, I think we argued that generically the pressure depends on the wall potential. There's no equation of state. The cases where you have an equation of state are interesting on their own as maybe toy models for building something more complicated, but that's not clear at the moment. The wall shape leads to varying pressure along the walls and to currents along the wall, and this leads to some instabilities of flexible objects, etc. And there's still a lot of interesting physics that's coming up by studying these physics, which we're exploring at the moment. So thank you very much for your time.